What's up, tous les personnes? Ça c'est Madame Sorensen with the mid-unit review. Let's get started. All right, here's some review of independent probability. Remember, independent probabilities are when two events do not impact each other. So for example, if you were to flip a heads on a coin, that would in no way impact what color you're going to spin on that spinner. All right, so for independent probability, we just multiply across. So what's the probability of getting a green on the spinner and then getting an orange? Okay, well, the probability of getting a green is 2 out of 12 because there's 2 greens out of 12. And the probability of getting an orange is also 2 out of 12. We could reduce those fractions first or just do it later. Multiplying across, we get 4 over 144, which reduces to 1/36. Okay, what's the probability of rolling a 6 and then a 6 and then a 6? Well, the probability of rolling 1 6 is 1/6. And the next roll, it's still going to be the same probability. And the next roll, the same probability. We multiply across our numerators, get 1, multiply across our denominators, and get 216. All right, the next one is the probability of heads, 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 heads. All right, that seems pretty unlikely, but let's see what the probability is. Each of these heads has a probability of 1/2 and is not impacted by the previous one. So we just have to multiply 1/2 times 1/2 times 1/2 times 1/2 6 times, or I could just raise it to the 6th power if I want. And that's going to give me 1 over 64. Right. Let's review a little bit about sets. All right, so for A union B complement, the first thing that I do is I highlight the A. So the A is going to be everything that is in the circle of A. Okay, now, what is in B complement? B complement is everything that is not in B. And I hope you remember this, but the best thing to do here is to circle the B and then to say, okay, I need to shade everything on the outside of that B. Okay, so that's going to look something like this. All right, now it's asking for the union, which means we put everything together. So our final answer is going to be everything except for that kind of moon shape figure on the inside of B. So let's go ahead and get our final answer for that. And it's not perfect, but you get the general idea. There it is. Okay. All right, the next one is an intersect problem. And notice how it's actually the same exact problem, but this time it's asking for intersect, which actually means that we want to find where both are. So let's go ahead and highlight, oops, wrong thing here. Okay, let's highlight A. So A is going to be all of this. And B complement, again, is going to be everything on the outside of B. Again, I like to circle my B and then shade everything on the outside. So this should look familiar from the last problem. And the real question for this one is where are they the same? Where's the intersection? Where is it both shaded, green and blue? And that answer is just that moon shape on the A. Okay, as you can see for that moon shape there. So I'm going to go ahead and color that in. Okay, so that's just going to be this shape. Right here. Okay. All right, next one here, very interesting. We've got a complement, and I like to deal with that at the end, but it's totally up to you what you want to do there. So let's go ahead and get A complement intersect B complement. So my A complement is going to be everything on the outside of A. Okay, and then my B complement is going to be everything on the outside of B. So that's going to look like, so I'm just shading everything that's not in B. Okay, so where do we see that we have intersection? Well, our intersection is kind of in that U section. It's everything on the outside. For example, it's all, it was all in this section right here. But actually, what did the problem ask for? It asked for the complement of that. So now I have to kind of do the complement or the opposite of that, which means I'm going to actually shade inside A and B. So my final answer here is going to be inside A, inside the intersection, and inside B. There we go, a little sloppy on the bottom there, sorry about that. Kind of need to, if I erase that, we'll erase everything. Oh, yeah, it sure did. Sorry about that. You can go ahead and fast forward the video if you want to skip through my drawings here. It just takes a little bit longer on the computer. I apologize about that. All right, moving forward, I think. All right, here we go. Get back to my black pen. So this was the die problem. What's the probability of rolling 2 die that sum to 12? Well, how many options do you have that does that? And that's just that one option right here. So that's just going to be one option out of the 36. What's the probability of rolling 2 die that sum to 3? Well, that's going to be 2 out of 36, and that's going to reduce to 1/18. All right, what's the probability of rolling 2 die that sum to less than 9? Well, that would be counting up all of these. And counting up all of those, I get 26 out of 36, which reduces to 13/18. All right, what's the probability of rolling 2 die that sum to an even number? Now, you're totally welcome to go through and just circle all the even, but I will tell you that your guess is probably correct, that half of these are even and half of these are odd. If you don't believe me, count up the circles that I just did and you get 18 out of 36, which is 1/2. All right, let's review some conditional probability here. Remember, this symbol right here means given. So what's the probability that you have a sports car given you're female? Remember, the numerator is that small circle. It's having a sports car and being female. So sports car and being female is right, nope, boy, I'm struggling. Sports car and female is right here, 45. So that'd be 45 divided by the total number of females. It's always divided by that last thing. Well, how many females are there total? There's 180. And does that reduce? Yes, it does. It reduces to 1/4. All right, next one. What's the probability of being male given you have a sports car? Well, for this one, we want to combine the male and sports car. Well, male and sports car would be the 39. Divided by the total number of males, which were going to be 60. Oops, sorry, I messed up on that. Divided by the total number of sports cars. Where's that sports cars right here? It's going to be 84. Sorry about that, folks. That's going to be equal to total number of sports cars. Yep. And that reduces to 13/28. All right, next one is combining SUV and female. So SUV and female is right here. So that's 135. And then divided by the total number of females. Okay, so our big circle is going to be here. And there's 180 females. So that's 135 over 180, which is 3/4. All right, let's review the at least one. Remember, that formula is the probability of at least one equals 1 minus the probability of not A. All right, so given any year, the probability that you see a moose in Manson is 3%. So I like to kind of write up here, probability of seeing a moose equals 0.03. Probability of not seeing a moose, or not moose, equals 0.97. Find the probability that you see a moose in Manson during the next 10 years. So that's the same probability that you at least see one moose during your next 10 years. So the probability of seeing at least one moose in 10 years is equal to 1 minus the probability of seeing no moose the first year, no moose second year, no moose third year, all the way up till you're 10. This you do 10 times, right? No moose, no moose, no moose. So what's that going to look like? That's going to be 1 minus, well, no moose is going to be 0.97 times 0.97 times 0.97, and I'm going to do this 10 times, or I can stop that nonsense and just say, hey, if I'm multiplying something by itself 10 times, I'm just going to have that raised to the 10th power. When I do that, I get 0.26257, and that reduces to a 26.26%. All right. All right, let's see what we got here. Mr. Fournier hits the dartboard 95% of the time. If he throws 20 times, what's the probability he hits the dartboard less than 8 times? All right, so 95% means we're in this category right here. That 95%. He's throwing 20 times, which is this right here. And we want to know what's the probability he hits the dartboard less than 8 times. So that would be like 7, 6, 5, 4, 3, 2, 1. So I find the 7, which is right here. Okay, and so it would be adding up all of these probabilities. Because it says less than 8 times, that's why I'm including 7. And so what is 0.00 plus 0.00 plus 0.00 plus 0.00 plus 0.00? Obviously, that is going to be a 0% chance. Way to go, Mr. Fournier. All right, here we go. What's the probability of rolling a number less than 17 with 3 dice? We've solved this exact problem before. It's kind of tough to mix these problems up just because the numbers get too big that you kind of have to limit it to this particular problem. All right, don't use your notes to solve this if you want to pause and try this on your own. All right, you're back. So what's the probability of rolling a number less than 17? Well, that's going to be 1 minus the probability of rolling something that is the opposite of less than 17. And if you're rolling 3 die, 6, 6, 6 is your max of 18, which means if you are less than 17 and you're trying to be opposite of less than 17, the opposite of that would be 17 and 18, right? Because 17 is not less than 17 and 18 is not less than 17. Okay, so we have to find the probability when we roll 3 die that we get a 17 and an 18. And how could we get a 17? Well, we could roll a 5, 6, 6, a 6, 5, 6, and a 6, 6, 5. And that's it. Those are only 3 options. How could we roll an 18? Well, just 6, 6, 6. So that's 4 options. But how many options are there total? Well, if you have got 3 dice, we do our counting principle. The first roll, we've got 6 options. Second roll, we've got 6 options. Third roll, we've got 6 options. So 6 times 6 times 6, what is that equal to? That is equal to 216. So what is the probability of rolling a 17 or an 18? Well, that's going to be 1 minus our 4 possibilities out of 216. So I can go ahead and have 216 over 216 minus 4 over 216, which gives me 212 over 216, which I reduce in my calculator, and I get 53 over 54. Fantastic. All right, you roll the dice 5 times. How many different possible outcomes are there? Well, this is a counting principle problem where you say, oops, sorry about that. Where you say, I've got 5 different slots, and on the first roll, I have 6 different options. Second, I've got 6, 6, 6, and 6. So we're just gonna multiply straight across with that. And it looks like we have 7,776 possibilities. All right, that's it, folks, for review. Hope you enjoyed.